welcome to Lecture 4. So, last class, we went over warm and cold cloud processes and how each type of cloud makes precip. We talked about the raindrop. We talked about cloud shapes and how they've got that flat bottom. We discussed rain, snow, sleet, and freezing rain formation by discussing the various vertical temperature profiles needed to form each. And we introduced the concept of stability. Important note, in bold, you need rising air to form clouds. Right now, we're going to talk about how we get rising air, but you need to remember why we need or care about rising air. So, key, rising air forms clouds. That's why we care about it, and that's why we want it in our storm formation. Great, so here's our parcels, and so I wish this wasn't in the way. Maybe if I stop moving my mouse, it will go away. So we have these little air parcels that form at the surface. They're like blobs of air, and if they're touching the ground's hot, and they will move up and they will expand to cool off. If the air is stable, so let's say the ground is cold or something, the air likes being where it is, and so if you try to move it, if you apply a force to it, it's going to snap back to where it was. If the air is unstable, if you give it a little push, it's just going to keep going up. So the unstable air will continue to move upwards, and eventually it will get to the point where it is cold enough to form a cloud, and it cools off by the expansion of the parcel due to the decrease in pressure as you move aloft. Finally, we have the neutral air parcel, which is you give it a little push and it's fine where you put it, but it's not going to continue to launch up. It's just going to stay where you put it. So here is a brief overview of the last class. If you want to add this into your notes, this is what I just said. So, no, it's not what I just said. Let's talk about this, actually, because this talks about the environmental temperature. So the environmental temperature and the parcel temperature are what's important for knowing if something is stable, unstable, or neutral. So remember, warm air rises, but what does that mean? It means that warm air rises relative to its surrounding air. So even if you have something that's considered warm, if the air around it is warmer, then it's not going to rise. It's not going to want to rise. So let's say your air parcel is colder than the surrounding environment. So that Tp indicates parcel temperature and Te indicates environmental temperature. The parcel is more dense than the surrounding environment, so it's negatively buoyant, and the parcel will sink, and clouds will not form, and it's a stable air mass. So parcel cooler than the environment, it's stable. It's fine where it is. It doesn't need to rise to cool off. It is fine. But let's say your parcel is warmer than the surrounding environment. The Tp greater than Te. Don't like that. The atmosphere wants to be in equilibrium. So it's going to rise to cool off. The parcel is less dense than the surrounding environment, and that's because the molecules are moving around faster in there. So it's positively buoyant. So it's going to continue to rise and accelerate upwards, and clouds will form. So this is the unstable air mass that we were talking about. Let's say that the parcel and the temperature of the environment are the same. The parcel has the same density as the surrounding environment. So it's not going to move on its own, but it will move if you push it. It's not going to snap back because it doesn't really care like where it is because it's in equilibrium. So it's happy wherever you put it, and it's not going to form clouds if there's not already clouds. It's just a neutral environment, not much going on. So what you really want for storm formation is an unstable air parcel. Showing this again, I guess. Yeah, so we just went over this slide. Well, they added a couple things. So the stable mass, so here, the parcel temperature is less than the environment. So this is like cold air outside, and this parcel is even colder. So you really get it to snap back to the ground. Like, it's a cold parcel, stable. It's not necessarily cold around it. I don't know why I said that. But air parcel temperature, less than the environment temperature. That's what's important here. In this unstable, the parcel temperature is greater than the environment temperature. So it's less dense, the air molecules are moving fast, and it wants to cool off. So it will move upwards. And in the neutral, they're the same, so it's happy wherever it goes. Stability. We're still talking about it. So how do we know if the temperature of an air parcel will compare to... How do we know how the temperature of an air parcel will compare to the temperature of the environment? The answer. Air parcels cool at predictable rates as they rise, especially if they're dry. And you can also look at a sounding, like a weather balloon, and it will also tell you what will happen. Oh man, okay, a lot of text, but we'll get through it. So, air parcels cool as they rise because they expand to match the lower pressure of their environments. We talked about this. So, rising unsaturated air parcels cool following the dry adiabatic lapse rate, the DALR. So adiabatic means closed. So we treat the air parcel like a closed system. So the only way it's going to cool and warm is if you change the volume of it, which will change the density of it. So if it's dry, it's unsaturated, and the lapse rate is the rate at which temperature decreases with increasing height. So remember that if the temperature is decreasing, the lapse rates are positive. So lapse rates are positive when they indicate decreasing temperatures. You can have a negative lapse rate, but that just means the temperature's increasing when it's rising. Dry adiabatic lapse rate, always the same. 9.8 degrees Celsius per kilometer, which is 5.5 degrees Fahrenheit per 1,000 feet if you don't like doing math. Because you can't really do math with Fahrenheit or feet, unfortunately. If parcels cool enough, they can cool to and pass their dew points and form clouds. True. So cooling decreases the saturation vapor pressure. So remember that vapor pressure over saturation vapor pressure is the relative humidity. So if you decrease the saturation vapor pressure, it takes less water vapor in the air, VP, to get it to reach saturation. So cooler air needs less water in it for a cloud to form. Actual water content, VP, remains the same. And that's because we're in this parcel, we're assuming no mixing, we're assuming no hydrometeor loading. The only thing that's changing is the saturation vapor pressure, and that's because the temperature cools. So it's not too hard, just cool it off and it's more likely to form a cloud. So, dry adiabatic lapse rate, more on it. Conversely, air parcels warm as they sink because they contract to match the higher pressure. So when you have a sinking unsaturated air parcel, they will warm at the dry adiabatic lapse rate. So the sinking motion prevents cloud formation by causing air to warm up and dry out. So this warming increases the saturation vapor pressure, the denominator, and it decreases relative humidity. So if you have a larger saturation vapor pressure, the relative humidity is going to go down. And the saturation vapor pressure is a function of temperature, and the vapor pressure is a function of how much water vapor is in the air. The actual water content remains the same once again, because it's adiabatic. So, long story short, if the air gets warmer but you have the same amount of water, it is going to have less humidity. That's why sinking air causes dry, high pressure systems. So yeah, this is always, when it goes down, it always follows the dry adiabatic lapse rate. Stability again. So knowing how an air parcel cools is only half the information we need. Oh, okay. True, because we need to know how the parcel's temperature compares to the local environment's temperature to determine stability. So how does the environmental temperature change with height? The answer is that the environment does not cool predictably with height. It's true. Its temperature changes in all sorts of crazy ways as a result of the time of day, the season, the location, and the movement of air masses. So that's why twice a day outside our beautiful campus They tie a piece of styrofoam to a balloon and they launch it off into the great unknown, and it collects temperature data, it collects humidity data, and wind speed and direction data, and it's pretty magnificent. It's like using a balloon to forecast the future. That's kind of awesome. Okay, so, oh, and that's right where we went. We're going to atmospheric soundings. So sounding is another name for weather balloon data. So in lecture 1, we saw that in general, the troposphere temperature decreases with height. This is just an average. It's highly variable, and the temperature can warm with height sometimes, and that's called an inversion. That's especially if you have like a warmer air mass moving in the mid-levels over like a colder ground air. Especially at night, you can get a temperature inversion, and they're not good. Like, they're good a little bit, but they're not good a lot. You want like a little bit of a temperature inversion that can break, but if you can't break a temperature inversion, you're not going to get a severe storm. So how do we know at a given time and location exactly how the environmental temperature is changing with height? Hint at the top. Okay. There's the weather balloon. They're so cool. Okay. Look, you got the little piece of styrofoam, and it's attached to the balloon. And they make it seem like the balloon is just like standing here, but these balloons, if you let them go, oh my god, they will rocket off. And I know I was on the tourist mission this summer where we went out into supercells and we were like launching these balloons, and we had like so many balloons that we accidentally launched. So typically weather balloons are released twice daily at National Weather Service forecast office around the US. So it's like around 100 balloons a day. Or 100 balloons at a time, twice a day. That's my prediction. I don't know for sure, but that's what I'm feeling. So yeah, so we have Raman sondes, or devices that can measure a bunch of atmospheric quantities. So we have thermometers to measure the temperature profile, hygrometers to measure the humidity, barometers to measure the pressure, and anemometers to measure the wind speed and direction. And they also have GPS on them, so we can figure out how far they travel from the site, because they're not going to go up in a straight line. They're going to get blown around. Here's a video of a balloon launch. There's so many videos on Twitter. I have videos of my own balloon launch that I sent to my mom. And if you take like an instrumentation class here, you can also do your own balloon launch, which is kind of fun. So yeah, weather balloon, awesome, provide us a lot of data. They have their own problems, but they do a lot for us. And also this weather balloon data is what gets spit into the models. So they take these weather balloons and all of this, and then they average it across the US, like for the grid spacing, and the models come up with what they think the forecast is going to do. So it's really important that this instrumentation is working right, or because a small error can generate large errors into the future. Okay, here are all the locations. Wow, so we've got our one in Oklahoma, KOUN, OU, University of Oklahoma Norman. Yeah, so Lawton, Texas. It kind of gets a little iffy when you get out to the Pacific, because you don't have like all of this, like you can't launch balloons out in the ocean, like that would be a lot of money and time. So we kind of have problems with model data when it comes to like the Pacific, but they do try to launch balloons out on the coast and stuff. And it's about 200 a day, I would guess. So Raman sondes make rapid measurements of the atmosphere. Yeah, so they keep like checking over and over what the profile looks like. And sometimes they can hit the troposphere, tropopause, and even the stratosphere before the balloon pops. we've had balloons that have gone out to like literally space, like on accident. Like, why is this up in space? I don't know. But yeah, the balloons get huge as they go up because the pressure decreases, so there's less pushing down on it. So it's kind of similar to the parcel theory, where the parcels expand when they rise. The weather balloons also expand when they rise. The balloon is also pushed by the wind, so it doesn't go up in a straight line. It moves around, and so that's how we get these things called hodographs, which plot the location and the wind speed of the balloon at different locations. Yeah, but it's not perfectly vertical profile, so it kind of can cause problems. Like, you can't really know exactly what's going on in a location above your head because the balloon travels. It can travel almost 200 miles from where they're launched. Okay, so this is kind of like a sounding. The data is collected and synthesized into tables, and then it's plotted. And the plots of the atmospheric variables with heights are called soundings. And the sounding is beautiful, wonderful, excellent, very useful. You will learn about it in your other classes if you haven't yet, and your life will be a lot easier. So this is kind of like what it looks like. So it has like the surface temperature up to 5 kilometers and the relative humidity. Usually they use dew point, and then the wind speed. So yeah, you remember these. Yeah, so this is what a sounding looks like. So this horizontal axis here, is the x-axis. It's the property being measured, so it's like temperature, and the vertical axis is the height above the ground, and we usually use pressure coordinates, so it will be organized by the pressure level and not the height. So here we have the environmental temperature profile, so the balloon's measuring the environment, and then the parcel data will be estimated based on how the parcels work. So like following the dry adiabatic lapse rate and then following a moist adiabatic lapse rate once it condenses. But this is the environment, so it can look all wonky, it can look all crazy. And this is it plotted, so it starts at 80, and then by 5 kilometers it's down to 68 degrees. So this asks the question, where is the temperature inversion acid right here? So the temperature inversion just means that the temperature is increasing with height. So we can see between the 3 and 4 kilometer levels, the temperature starts increasing with height. This is a temperature inversion. It looks like a nose. And yeah, we'll get more into the importance of temperature inversions later in this class. Yeah, so they inhibit cloud formation. And as the parcel rises and cools, it must stay warmer than its environment to keep on rising, but it's kind of hard to do that in an inversion. You can get rid of it, and if you can like get a parcel to break through the inversion, it's called like a loaded gun, and it can make for some really powerful storms. But if you have too strong of an inversion that it can't break through, it's not good. You will not get any storms. So inversions are typically stable layers. They're called a cap. Yeah, so like a capped sounding just has an inversion in it. It just has a layer of warmer air. So this means that the entire stratosphere is on average a stable layer. And that's why the weather stays in the troposphere. So once you get up, I would go back to the last lecture, but that would be a lot of work. Once you get up to like the stratosphere, it starts warming up. That's where the tropopause is where this temperature like stops cooling and it starts warming up. And it's like farther up here. It's like 12 kilometers or something. Yeah, that is, you're not going to get any weather to form past that because it's heating up due to the ozone layer. Often, inversions form at the top of the boundary layer during the daytime. So, yeah, because a free atmosphere is not really it's kind of like, I'm going to skip that point. I don't want to make things more confusing. So, inversions form at the top of the atmospheric boundary layer during the daytime. So the atmospheric boundary layer is the lowest kilometer of the atmosphere. If you want to take a class that's really hard, take graduate level boundary layer, and you can learn all about it and leave the class and realize you don't know anything at all. But yeah, it's the layer in closest contact with the ground, and it prevents air parcels from rising high enough or cooling enough to form clouds. And it can also trap pollution. Yeah, so if you can't get this air to rise and mix out, then the air pollution stays stuck, and it's unfortunate. I don't understand. Usually the inversions, they form at the top of the boundary layer during the daytime, but the real inversion is during the nighttime because the ground gets cold and then you have this warm air at night above it, and so you can't really get it to push past the warmer air that hasn't cooled off yet. And that's just because the ground cools off faster than the air above it, and that's a specific heat thing. Also, about the boundary layer class, you can do it. If you take that class, you can do it. You're just going to have to take a few classes beforehand to be ready for it, but you will learn stuff in that class. It just kind of stretched my brain quite significantly in ways I thought were not possible. Okay, here we go. This is the top of an inversion. That is nasty, and that stuff, like that haze and stuff, shortens the lifespan of people. So I suggest you live in a city that has less air pollution than that. But yeah, you can see there's a temperature inversion here. I can't believe this is real. I guess it's a Wikipedia source, and I trust Wikipedia, so yeah, it's pretty bad. So you have this inversion layer, and it's like trapping it, because this air up here is warmer, so it can't rise. It's like a stable air mass down here, and it's stuck. That's so nasty. Okay. Let's talk about stability a little more. So, I hope, if you're colorblind, I'm really sorry, and this blue is the parcel temperature that is just following the dry adiabatic lapse rate and until it reaches saturation, in which it will start looking more like a curve. But in this example here, it's just following the dry adiabatic lapse rate. And then the environment's just doing whatever it wants. So when the parcel temperature is less than the environmental temperature, it is stable. When the parcel temperature is equal, it's neutral. And when the parcel temperature is greater than the environment temperature, it is unstable. So honestly, if the blue line here on the right, this parcel, if it is to the right of the temperature line, it's unstable. When they're crossing, they're neutral, and when this environment line is to the right of the parcel, it is stable. So, yeah, the temperature of the environment behaves erratically with height, and the dry parcel's temperature decreases with the DALR. So can you label the stable, neutral, and unstable? I wonder if they'll do it for us. There we go. Okay, yeah, so here we go. We have this unstable down here because the blue line is farther to the right. It's warmer than the red line, the environment. When they cross, it's neutral, and then this is stable up here because the environment temperature is warmer than the parcel, so it's not going to want to rise anymore. Okay. Yep, so we talked about the rising of unsaturated air parcels, but what about saturated air parcels? So this brings up a topic of the LCL. So this is where the temperature is equal to the dew point temperature, and this is where the parcel becomes saturated. That's the LCL, lifting condensation level. This is where the cloud base forms. This is why the bottom of the cloud is flat. That's because the LCL is just a line. It's a line in the air where the clouds form. So, rising saturated air parcels cool at the moist adiabatic lapse rate, which is kind of changes with height. It looks like a curve, but it's around 6 degrees Celsius per kilometer. So, remember, it's adiabatic, so it's a closed system, and it's moist, meaning it is saturated. And the lapse rate is the temperature, how much it decreases with increasing height, and it's positive when the temperatures are decreasing. So the moist adiabatic lapse rate, like I just said, is around 6 degrees Celsius per kilometer, which is about 3.3 degrees Fahrenheit per 1,000 feet. So it varies throughout the troposphere. Why is the MALR not the same as the DALR? This is because water changes temperature slower than dry air. So if you add water into it, it's going to cool off at a slower rate, which is good for a parcel. Okay, it's due to latent heat release, and this is when water vapor condenses into liquid water. The molecules release some energy as heat. This energy warms the air and counteracts the cooling due to rising motion. So the parcel cools less rapidly. Okay, so it's a condensation thing. So condensation is a warming process, and so yeah, it counteracts the cooling. And also water just doesn't change temperature as fast. It's because this is happening as well, like because the water is changing state, it's not heating up as fast. It doesn't mention that in the slide, but that's also the case. Anyway, long story short, moist adiabatic lapse rate is less than the dry adiabatic lapse rate. It's going to cool off slower if the air is moist. Moist adiabatic lapse rate less than dry adiabatic lapse rate means that saturated air parcels cool less rapidly than unsaturated parcels. Saturated parcels are therefore more likely to be warmer than the environment than unsaturated parcels. This is true. This is true. If you have an air parcel that's saturated, since it's not going to cool off as fast, it's going to be more likely to be unstable. A rising saturated air parcel therefore has a higher chance that it will continue to rise. Another thing also not mentioned in this slide, but I will mention it to you because you all are so big-brained. Water vapor weighs less than dry air. So if you have a moist parcel, it's also going to rise because it weighs less. And because it cools off less fast. So that's a double whammy. If you have a moist parcel and a dry environment, that's very good for storm formation. Takeaway, rising saturated air parcels are more likely than rising unsaturated air parcels to produce precipitation and storms. Density. Oh, yes. Okay. Well, they want you to be big-brained anyway, so we're going to talk about it now. So far, we've been connecting density with temperature. Warm air is less dense, cold air is more dense. But moisture also plays a role in density. So, for a constant temperature, is moist air less dense? Moist air is less dense than dry air. Not a question, an answer. Moist air is less dense than dry air. Wait, what? Yeah, it's true. They made us calculate this on the first day of class, pull out a periodic table. Here we go. And if you want to do this math, be my guest, but just know that these molecules for water weigh less than nitrogen and oxygen. So, yep. Less dense. And because of that, air that is warm and moist is the least dense type of air. And air that is cold and dry is the most dense. So if you have air that's cold and dry, or warm and dry, and the air around it's warm, just forget this point. Anyway, cold and dry air sinks. And if the environment around it is warmer and moist. And the air is sinking here right now, and it is very dry, and there's moist air all around us, but it seems to not rain in Oklahoma. The air is sinking here, and we will never see a cloud ever again. Okay. So, takeaway, an air parcel that is both warm and moist is the air parcel type that is most likely to reach saturation, because it's most likely to rise freely and form clouds and storms. Also, if an air parcel is dry and warm, like if it's super dry, even if it gets up into the atmosphere, like it's not going to condense as quickly if it has less water in it. So that also makes sense. So we often see clouds, rain, and storms on days where the air is warm and moist. So think about April, our favorite month, or May if you live in Oklahoma like me. Think of your typical April or May severe weather day. It's muggy and hot and gross. The perfect weather for precipitation formation. And that is true. That is true. Oh, wow. Great. This is what it looks like in Oklahoma. I wonder if this is Oklahoma. Can we view the source? Okay, it's a fake link. Okay. Anyway, this is what it feels like when I step outside. Stable environments often lead to clear blue skies. Clouds that do manage to form are short and flat. They're shallow. and shallow clouds are less likely to produce precipitation. So you've got a lot of sinking air in here, and it's just hot and not great, not fun. This beautiful pixelated cloud, very beautiful though, tall, deep cloud. This indicates an unstable environment. Clouds are tracers for air parcels. And so you can imagine the top of this cloud is where the air parcel is at, and this is like where the air parcel has been. So they extend up high, and the deep clouds are most likely to produce precipitation. They're very heavy. And also lightning comes primarily from deep clouds. This is because the lightning forms when you have like liquid and ice in the clouds that kind of absorb the charges and create like a big battery. So you want a lot of liquid and a lot of ice in a cloud interacting so you can get lightning formation. Okay, that's the end of PowerPoint 1. We got a couple more. Okay. We talked about stability, we talked about soundings, and we talked about dry and moist adiabatic lapse rates. And the dry adiabatic lapse rate is greater than the moist adiabatic lapse rate because the latent heating from condensing water into water vapor in moist parcels counteracts some of the cooling from rising. Okay, this is fun. This is awesome. This is epic. This is what we're here for. We're going to talk about forces. We're going to talk about fronts and mid-latitude cyclones. Great. Okay, forces. So a force is an interaction that causes a substance, including the air, to change speed and or direction. Too long, didn't read. A force causes an object to accelerate. Great. Here are all these different types of forces. Yeah, you can read that if you want. Gravity's kind of important. It causes objects to fall down towards a bigger object. Also, magnetic force. I took physics 2 in the lovely spring of 2020, and I gotta say, I don't get it. But I'm glad that there are people out there who do get it. It's not me. That was not my calling. Anyway, so we learned about these air masses, and we moved that these air masses moving away from their source region and into other region is what generates weather. What causes the wind? The pressure gradient force. What is the pressure gradient force? It's when you have two different pressures and high pressure goes towards low pressure. That is what creates the wind. Okay, this is me and the friend that I don't have. You guys can be my friends. Anyway, pressure gradients is a gradient is the change, either increase of or decrease of some quantity over a distance. So comparing the atmospheric conditions at your location versus your friend's location. So the temperature where I'm sitting in my room and where you are sitting, let's say the temperature is different, but the dew point is the same, and the pressure is different. So since the temperature is different, there is a temperature gradient. The dew point's the same, so there's not a dew point gradient. But the pressure is different, so there is a pressure gradient. So we learned that atmospheric pressure always decreases with height. True. Pressure may increase, decrease, or stay the same on the horizontal. So we're talking about like on one level, like how the pressure changes. This is because of uneven temperature and moisture distribution from around the world. So pressure is increasing from northwest to southeast. Okay, yeah, so you have like 1016 millibars up here, and down here it's like 1020. And they have this nice rainbow schematic. Yeah, so the pressure is just increasing. So this is a pressure gradient. And I think they added the colors in to really show like the gradient effect. Again, I will shout out the Oklahoma Mesonet app developed at our school. Very useful. Highly recommend the app. Okay. Pressure gradients. So high pressure, H, H for high, L for low. And this is like relative to like their immediate locations. So low pressure systems, this is what we like to see. We like low. These are called cyclones. And the high pressure, and they rotate counterclockwise. Sorry, they're going counterclockwise. And the high pressure rotates clockwise, and it's pushing air away, while low pressure is kind of like sucking air in. Key fact, pressure changes in the horizontal create the wind. Yeah, like we said. Okay. So, little PGF tutorial. So, this is the force that causes wind to blow outwards from a high pressure and inward towards the low pressure. Yes, so it's like blowing up a balloon, and you have a high pressure inside and a low pressure outside, and the air just wants to be in equilibrium no matter what. So it's going to move towards the low. It's going to try to fill that in. And it's going to move away from the high because it's pushing on it too hard, pretty much. So PGF is the fundamental driver of wind. It's what causes the wind to blow. It also creates these big systems that we were talking about. So let me go to the back to the last one. So you see this one right here, this little blue with the triangles, that's a cold front. This is a stationary front, but you can kind of assume that it's warmer air up here. So let's just say it's a warm front here. What's going on here is this low pressure here is pulling in air. It's pulling in this cold polar air mass that's coming up from Canada and the poles. Not cold polar, continental polar. I will do that, and I will continue to do that, and I don't know why I do that. But anyway, it's pulling this air in, this cold air, and then it's also pulling in this Gulf moisture. So I guess we have warm air down here. It's stationary, but it's still warm air. It's just not moving. So you have this setup where you have cold air and warm air and these two air masses are meeting at this cold front here. And that's where we're going to get the storm. I'm sure we will get to that soon. But that's the importance of the low pressure. Okay, low pressure. Partial vacuum due to lack of air molecules. And high pressure is abundance of air molecules. So air from the high pressure center flows to the low pressure center. Thus, the difference in pressure, the pressure gradient, if it's stronger, the wind will... Okay, sorry. I read that sentence wrong. But the greater the difference in the pressure, the stronger the wind will blow. So if you have a higher high and a lower low down here, the wind's going to blow super fast. The PGF is proportional to the difference in pressure. So that's why in like hurricanes, the wind moves so fast. The center of a hurricane can have extremely low pressure. Like in the upper 800, maybe it's like 900, lower 900s. Lower 900s. I will say that. Okay, quick summary. Pressure gradient. Difference in pressure between two locations. PGF is the force that drives the wind from high pressure regions to low pressure regions, and it creates the wind. The PGF creates the wind, but what changes the wind? Coriolis. Remember that the Coriolis will deflect winds to the right in the northern hemisphere and to the left in the southern hemisphere, and it acts to turn the wind. So it doesn't create the wind, it just turns it. Friction. So when you're near the surface, especially in the boundary layer, it's going to act opposite to the direction of motion. So it's like the motion's trying to go this way, but the friction's going to hold it back some. It's going to stop it from going so fast. So the orientation of this force is in the opposite direction. If the motion force is greater than the friction force, so it will continue to go this way, but the friction force is in the opposite direction, so it acts to slow it down. Example, pushing a textbook across the table, frictional force opposes the book's motion and slows it down. But if you put a bunch of butter on the book or something, it's gonna get rid of some of that friction force and it's gonna slide really fast. Or like, maybe like ice skating, and after they use the Zamboni machine and it's like too slippery and you fall. Well, that's what happened to me. I'm projecting. Anyway, frictional force acts to slow down the wind. So that's why winds at the surface are not as fast as winds in the upper atmosphere, because you have greater pressure differences up there and no friction. Okay, friction force is too small in the free atmosphere above the boundary layer to noticeably slow down the wind. Due to the lack of structures, buildings, landforms, etc., friction force primarily slows down winds in the boundary layer. Okay, so down here, where we live, that's where it slows it down. 3 forces affecting the wind. PGF creates the wind, Coriolis turns the wind, and friction slows down the wind. All 3 of these forces act in the boundary layer. Only PGF and Coriolis act in the free atmosphere. PGF. The wind blows outward from a high and inward towards a low. Coriolis. The wind is deflected to the right relative to motion in the northern hemisphere. Okay, in the free atmosphere, only the PGF and Coriolis affect the wind, so this leads to the perfectly clockwise anticyclonic high, so it's moving like this, like a clock, and counterclockwise cyclonic low in the southern hemisphere. So this is how you get this, the Coriolis force, you can see it really easily with a hurricane. It also is the case for storms that are on a larger scale, like mid-latitude wave cyclones. So this balance here with the PGF and Coriolis, when they're perfectly balanced, this is called geostrophic balance. In the southern hemisphere, it deflects winds to the left and the winds turn the opposite direction. So we're focusing on the northern hemisphere. That's where the cool weather is for the most part. That's where we live. So, like in the northern hemisphere, counterclockwise is your friend for the low pressure, and clockwise is the high pressure, and it's reversed in the southern hemisphere. So, yeah, PGF, wind blows outward. This is in the boundary layer. This is near the surface. The wind blows outward from the high and inwards towards low. Then the wind is deflected towards the right in the northern hemisphere. And then the friction slows down the wind. So when you have friction, if the wind slows down, that means the effect of Coriolis is going to be less. So you're going to have less of this rotation near the surface than you are in the upper levels because the wind's going to move slower. So the circulation will not be perfectly circular like in the free atmosphere. And it doesn't have the friction does not have an effect on the pressure gradient force. It just has an effect on wind speed and Coriolis. So, in the boundary layer, the balance of PGF, Coriolis, and friction creates surface winds that flow clockwise and outward from the high, and counterclockwise and into the low. So instead of around the low perfectly, they're going to just flow into the low. So this is for the northern hemisphere. Convergence is wind blowing in towards each other. So, like, think of if you, like, pushed a bunch of wind together, or, like, a bunch of cars meeting at an intersection, that's convergence. Divergence is wind blowing outward. It causes a net outflow of air. So, people leaving Lloyd Noble after a basketball game. Yeah, they're all going to go out to their cars and go home and diverge and go away from each other. So, these are important concepts for the atmosphere. Convergence and divergence again. So convergence happens at the surface low pressure center. So you have this low here, and the air likes that. It wants to go towards this low. And so these two air mass, this like two air direction is going to come from all directions really from the surface, and it's all going to meet up at this low. And what happens when all these air masses meet each other? Well, think of what happens like when you have put your fingers together and you press, like your fingers move up or something like that. Like if you push two things together, you're going to get this upwards motion generated. It can't push down into Earth's crust. Like they pile up and they have to go somewhere, and so they have to go up. Rising motion through the depth of of the troposphere happens above all surface low pressure centers. Remember, rising motion creates cooling and moistening, which generates clouds and precipitation. So you have to have this rising motion here to form clouds. Okay, divergence happens at the surface. So remember, we're talking about surface convergence and surface divergence. So divergence at the surface happens at a high pressure center. So this starts and you have like air that is being pushed down and it flows out to both sides. Or you have air that moves outwards and then it has to fill in the gap, and so it creates sinking air. So the air sinks from above. And the sinking motion through the depth of the troposphere happens above all surface high pressure centers. So sinking motion leads to warming and drying. So this is following the dry adiabatic lap straight down, and you're going to have clear skies. That's why if you have a surface high, there's not really going to be any storm formation, unfortunately for us, sitting in Oklahoma in 100-degree heat. Okay. Great. So here's a nice diagram. So yeah, if you're at the surface at the low, it's kind of going in counterclockwise. They're converging, and there's going to be rising motion. At the high pressure, the air is going to be moving away, and so it's going to cause the sinking motion to fill in the quasi-vacuum. Okay, how are the horizontal winds blowing at the starred locations? Let's find out. Okay, so here you go if you want to fill this in. I don't really feel like I need to go over this, but if you have any questions about this, let me know. It's just, you draw a circle that is clockwise around high and counterclockwise around the low, and you can figure out what direction the wind is going. Okay, so concepts about surface pressure. Concepts about surface pressure's association with rising and sinking motion can be applied to what we already know about the global atmospheric circulation. That's true. So you have here at this Hadley cell, at the ITCZ where the Hadley cells meet, you have this rising motion, and it's going to form a surface low. Between the Ferrel cell and the Hadley cell, you have the sinking motion, so it's going to form a surface high. And then, again, between the Ferrel and polar cell, you're going to have this rising motion, which forms a low, and then sinking motion at the poles, which forms a surface high. So, ITCZ and polar front is surface convergence and low pressure. High pressure areas are where the winds are diverging at the surface and the air is sinking, so like at the Horst latitudes and at the poles. Okay, and we'll move on to our final PowerPoint of the day. Loading. Okay, so we're going to talk about, we talked about the forces in the boundary layer, three in the boundary layer, 2 in the free atmosphere, so you're neglecting friction in the free atmosphere. And we talked about how air circulates around the high and low pressure centers when they're in the boundary layer in the free atmosphere. So the wind speed slows down in the boundary layer comparatively, so the Coriolis force decreases. Okay, and we talked about how air rises or sinks through the depth of the troposphere above the low, high pressure centers through. Yeah, I don't really know. Anyway, rising air does not penetrate the stratosphere because the stratosphere is stable. Yes, so you have the air that's warming up above it, so weather kind of happens within the troposphere. It's because the temperature increases with height there. Why does air not sink from the stratosphere above a surface low at the pressure center? And where does the rising air go? And where does the sinking air come from? I love this diagram. This is the jet stream. So, are they going to answer the question? Well, here's the answer. If you took air from the stratosphere and you were to, you can kind of do this. It's called tropopause folding, but it's a little confusing. But the air from the stratosphere is stable, basically. So if you pull it down towards the surface, like, it's gonna rise back up just because it's stable. So instead, you're just gonna have air from the upper atmosphere fill it in instead of sinking. It's not like the day before after tomorrow or whatever. The professors love to bring that example into class. I've never seen that movie. I'm sure it's awesome though. Okay, the jet stream. Beautiful rope looking thing. So it's a long and narrow corridor of extremely strong winds near the top of the troposphere. So, very long, 1,000 to 3,000 miles, 200 to 300 miles wide, and it's 1 to 3 miles deep. And they encircle the globe, and they love going through the United States. Thank you, Jetstream, because this thing creates really good weather, like good, like bad, but like good for us. So, typical wind speeds range from 55 to 250 miles per hour. This thing is moving, and it must be at least 55 miles an hour to be called a jet stream. This is where the two air masses meet. This is where the Ferrel cell and the polar cell meet. I'm sure they will talk about that. Maybe not. Okay. Great. Here's the jet stream and a mountain. All right. Jet streams form high above the separations between warm and cold air masses. So they're like up there, like you can see they're like at the tops of the clouds. They're not at the surface. They're in the free atmosphere. And so they form at the separations between warm and cold air masses. So we have the subtropical jet down here in Florida style, and then we have polar jet more up north, but they move around. They do move around. And these separations are most consistently pronounced at the horse latitudes and the polar fronts, so that's those two. Consequently, there are two primary jet streams in the northern and southern hemispheres. So the polar jet stream is above 60 degrees north and south, and the subtropical jet stream is above 30 degrees north and south. And the wind speeds are strongest where the surface temperature gradients are the greatest, because the pressure gradient force is strongest. So the temperature gradient between the Ferrel and polar cells is stronger than the temperature gradient between the Ferrel and the Hadley cells. So that means that the polar jet is going to move faster than the subtropical jet. And the subtropical jet disappears in the summer because the Ferrel and Hadley cells have a small temperature gradient. So it's more of a winter time type of jet. Here it is in the beautiful weather map. And they're really good at making weather. They really are. These jet streams, this is so great for the United States for weather formations. They're not straight. They form ridges and troughs. So they meander north and south to line up with the greatest surface temperature contrast. Yes. So in the northern hemisphere, they tend to occur further south in the winter and further north in the summer. That's why this kind of thing is like channeling all this cold air from the poles. This polar jet, like it really pulling in this cold continental polar air. And so this is what we're getting in the springtime, like this kind of profile. But during the summer, this thing meanders north. And so that's why you really get severe weather events in Canada in the summer, while down here we get our severe weather events more in the springtime. And in Mississippi, which is all the way down here, we would get severe weather events in like January through April. Yeah, and you can see the jet stream on the 300 millibar maps of wind speed. So this is the top of the troposphere. So if you just go to like pivotal weather and you click on 300 millibar isotox wind or whatever, you can see this, and you can see where the jet stream is. And it's very good. If you have this U-shaped trough, that's what you're looking for to get severe weather. Jet stream is connected to the pressure centers, so the winds of the jet stream converge above high pressure centers by slowing down. The air builds up and converges and must go somewhere, so the air sinks down. The winds in the jet stream diverge above low pressure centers by speeding up. Air evacuates, diverges, and must be replaced from below, so air rises up. So, yeah, low pressure causes the air to speed up and diverge aloft, and the air converges aloft, you have sinking motion. It's just about a vacuum. So, like, up here, you kind of have a vacuum if there's divergence aloft. So, divergence aloft creates convergence at the surface, and that's at the low. This is called Dyne's compensation or something like that, if you want to look more into it. But yeah, just know that, like, if you have divergence aloft, you have convergence at the surface to fill it in. And if you have convergence aloft, the air sinks and you have divergence at the surface. So I think it starts with surface divergence and then it fills in. Okay, so we kind of talked about all of this. If you want to fill this in the notes, feel free, but I don't want to waste any more of your time. We'll just finish up this PowerPoint really quick. So, divergence aloft is typically strongest on the eastern side of the southward dip in the jet stream. Okay, so this is over like here. So this is where you kind of see the severe weather forming a lot of the time, like near this low, like down here. So this is where the surface low pressure typically forms. So you have this U shape. It's over on the right hand side over to the east, this low. Low pressure is attached to the enhanced divergence aloft in the jet stream, so it moves west to east with the jet stream. Yes, this low pressure advects, so it moves this way with the jet stream. Remember, jet streams exist on strong temperature gradients, so you have to have this cold air up here and this warm air down here. And sometimes over here you'll get warm, dry air, and that creates even more fun scenarios. Okay, now that we have this trough set up from the jet stream, we can talk about the mid-latitude wave cyclones and fronts. So, advection. This is the transport of any atmospheric property, so temperature, moisture, pollution, by the wind. So advection just means the wind moving across a flat plane. Advected atmospheric property moves in the same direction as the wind. Surface winds advect air masses away from their source regions, creating weather. Knowing the wind direction and location of air mass source regions tells us a lot about the weather. Yeah, so if it's cold up here and it's moving south, that means that you're just going to have cold air moving south, and that's pretty much that. It's not too difficult. How would the local weather conditions change if the wind was the yellow arrow, the red arrow, the purple arrow, and the orange arrow? So, in the yellow arrow, we have this maritime polar moving into maritime tropical, so the temperature would decrease in California. The red arrow here, we have continental tropical moving into maritime tropical, so you have a drying effect where this source air mass, this continental air mass, dries out the air down here. Now, if you have a cold polar air mass and it moves down towards the maritime tropical, this means that the air is going to cool off and you're going to have a cold front. So, the source region impacts where it moves to, where it advects to. If you have a maritime tropical out in the Atlantic and it moves north towards this maritime polar, it's going to heat up the air because this tropical air is going to move in where the polar air is, and it's going to be like a warm front. Okay, yep, so there you go. So this up here, These northerly, northwesterly surface winds advect cold, dry air southward from Canada. Westerly and southwesterly surface winds advect warm, dry air from the Rocky Mountains, desert southwest, and Mexico. So these orange arrows right here are warm and dry. So you have a cold air mass up here that's dry, a warm air mass that's dry here, and then these southerly winds here bring in like this warm, moist air mass, a maritime tropical mass from the Gulf of Mexico. And then this doesn't really happen, these gray ones, because there's the Appalachian Mountains, and you don't really get these easterlies. They kind of get blocked. So it's mostly these three air masses at play. So the surface winds blow clockwise and outward around high pressure, and they blow counterclockwise and inward around low pressure, and these winds also advect air masses. So the red and blue lines on the weather maps are called fronts, and I kind of talked about this for a minute. So fronts are boundaries between air masses of different temperatures. So where the line of the cold front is drawn, so this is this blue line here with the triangles, this is the edge of the air mass. This isn't like the center of the air mass, this is the edge of it. And that's where the important weather happens, is on the edge of air masses. So, there are areas of high temperature gradient, and fronts form as air masses are advected away from their source regions and come close to one another. So, yeah, this is like the edge of the air mass, and it's not in its source region anymore. Its source region's up in Canada, but it's been advected down into Texas. And this right here is stationary front, but its air mass comes from like the Gulf. So it's standing, if these are going the opposite directions, it means it's like it's standing still, but and these red ones right here are warm, but you can assume that the properties of this air mass, based on its location, are going to be warmer than this air mass. So this cold air mass is moving into a warmer air mass. Also, these orange line right here, this means a dry line. So this just means that the air is dry. Like it's cold. Usually it's cold. Sometimes it's warm, but it's dry. And dry air and cold air operate similarly in the atmosphere because they are both dense. So you can get dry line storms and you can get cold front storms. It just depends on your setup and the time of year. So note that the fronts are attached to these low pressure centers and not the high pressure centers. That's because they're diverging at the high pressure, but they're pushing the air masses away from each other. But in the low, the winds are converging at the surface and they're pulling these air masses together. Okay, so fronts. So you could say that these like cold air masses up here, CPCA and MP air masses, they're forming over Canada. If you had like a low here, you do often get lows here. They form off the Rocky Mountains. And then you have like the red here, it's like the warmer air masses. So you got a lot of cold and a lot of warm that are circling this low, and it makes for a good especially good setup for severe weather. So the Rocky Mountains and the combination of temperatures are really what sets us up for success here. So remember that the fronts are the boundaries between air mass. This is like the warm, moist air. People call this the moisture tongue, and it's really funny because it does look like a tongue in this drawing. So you get this warm, moist air. This is usually Gulf air. And these are the sharp temperature gradients right here. This air mass is completely different than this air mass. And so the type of front is determined by the wind direction. So a cold front is when the wind is blowing from the cold towards the warm. So usually you have the cold air over here and it's blowing towards the east and it's blowing into this warm air mass. But this is a warm front because this warm, moist air is blowing into this cold air. So it's what the air is coming from, like where it's coming from is where the boundary is drawn and what type of boundary it is. So here's a warm front. It's a warm air mass advancing towards a cold or cool air mass. So the front marks the boundary between the warm and cold air. So the cool is up here, and it's warm blowing into cold. So that's the warm front. And it's denoted by a red line with red half circles pointed towards the colder air. Warm fronts typically extend east to west, and they are associated with southerly winds behind the front. So yeah, and that makes sense because it's Gulf of Mexico air. So usually it's just moving up north from the Gulf, and they look kind of like this. So the warm air is less dense than the cool air it's blowing into. So it rises above this cold air, and it's a gradual rising motion. There's not really that much force behind it. It's just gradually rising. So this can happen. This can lead to light precipitation. And usually you get like stratiform clouds, which are just clouds that are they cover like the whole sky. It's warm everywhere, and it's just like a rainy storm that is widespread, and it's not raining too hard, and you're not going to get like tornadoes or anything off of this. This is just like a warm front stratiform cloud. So storm, like, it occurs on like the cold side of the front usually, this precipitation. They can form along warm fronts. It's less likely. Signs of a warm front has passed. You know you're in a warm front when the temperature especially, this is especially true in the springtime. Like, these fronts are very prominent in the spring. If you see a increase in temperature, in dew point temperature, the wind shifts to a southerly wind, so wind that is blowing from the south, and the sky changes from a cloudy sky to a clear sky. So if you're in here and it's warm outside, you're probably in a warm front. But warm fronts are usually followed by cold fronts. And if you have a warm front and then you check your phone and you see that the temperature's going to drop this week, it means, not this week, we're not getting a cold front. I'm sorry. It's the summer. But if it was springtime, and you see that, the temperature is 70, and then next week you have a temperature in the 30s, you're like, okay, a cold front's gonna come through. So a cold front is a cold air mass advancing towards the warm air mass. So you get the warm air mass first, and then you get the cold front. This front marks the boundary between the cold and warm air. Said that a lot in this PowerPoint. It's denoted by a blue line with blue triangles pointed towards the warmer air. Cold fronts typically extend north to south and are associated with westerly or northerly winds behind the front. Yeah, so it's just cold air coming from the poles or coming from the west. You have this cold air, and you have warmer air that's moving. It's southerly, so the air changes direction between the warm front and the cold front. Here's a nice schematic. The cold front is the bread and butter of severe weather. This is really what gets it going. So the cold air is more dense than warm air, and it pushes the warm air up and over. So the rising motion is very sudden. So it kind of digs up under this warm, moist air, and it forces this upward motion. And this air is moist, it's warm, it's moist, and it's unstable, and it's gonna want to rise. So when you have this forced rising motion, it's gonna do so even more. And just along this cold front boundary, you can get some very severe storms. So this sudden rising motion leads to heavy rain and intense storms. Precipitation occurs on the warm side of the front. So it's not in this cold air mass, it's out in front of it a little bit. Like, it pushes it up, like, out in front and forces this upward motion before it gets to the cold. So, like, in comparison, like, you're out over the cold air in the warm sector and it looked like that, but for this, it's out in front of it. You can get lines of heavy storms, like squall lines, but this can also generate supercells if the storms don't run into each other. Signs the cold front has passed overhead: a decrease in temperature and dew point, a wind shift to westerly or northerly winds, and the clouds thicken overhead, possibly in a linear formation with embedded storms. So it's pretty easy to tell when a cold front will come through. Like, you'll have warm days and then you'll see the temperature drop, and when I see that, I'm like, okay, there's going to be a storm. Usually these cold fronts have storms along them, and so it will go from warm, you'll have an intense storm, and then it will be very cold the next day. The stationary front. We saw this on that diagram. So this is a motionless boundary that persists between warm and cold air. So neither warm or cold air is advancing, it's just staying in place. So you have cold air up here, warm air down here. So it's denoted by blue and red dashed line, with blue triangles pointed towards the warmer air and red circles pointed towards the colder air on the red dashes. So you can still get precipitation here. Warm air is still rising up and over the cold air. Yeah, so a place that gets a lot of stationary fronts, like Japan, like during the monsoon season, they have a persistent stationary front that results in weeks and weeks of rainy weather. And we do get these sometimes in the United States, and even if you have a stationary front out front instead of a cold front, you can, or instead of a warm front, you can still get a severe weather setup. Whoa! Okay, Frontzilla. Since fronts mark the boundaries of air masses, they mark the location where the temperature changes very quickly over a small distance. Yeah, so this is cold front. It's just the edge of this cold boundary here. So it's like in the 70s here, and it's 27 in Colorado. If there is a blizzard in Colorado in the spring, you can bet that there's probably going to be severe weather in the next day or so here. So here's your example. I guess there's an example here if you want to supplement the lecture. And this is cold front. Yeah, so it's just cold air blowing towards warm air, and it's the leading edge. And this leading edge right here, right out in front of it, this is where that storm is going to form. And I think that's it. Let me make sure there's not another one. Okay, we are good to go for today. So thank you for attending this lecture, and I will see you tomorrow.